The following is a presentation of exam wrapper number 2, problem number 4, in which you put a thin metal pot containing 2 kilograms of room temperature water on a hot electric stove. You also stir the water vigorously with an electric beater, which does 100 joules of work on the water every second. You observe that after 15 minutes the water reaches a temperature of 100 degrees Celsius. Note that the specific heat capacity of water is 4.2 joules times grams over degrees Celsius. So in this question there's 4 parts. In part A, you have to determine the change in thermal energy of the water. Part B asks you to find the thermal transfer of energy Q from the surroundings into the water. And part C wants you to find the change in energy of the surroundings. And then last, part D asks you to find the final temperature of the mixture of sweet potatoes and the water which after has boiled and once it has reached equilibrium. So in part A, before we start doing any calculations, we must first acknowledge the parameters given by the problem. We know that 2 kilograms of water were boiled at room temperature, or boiled starting at room temperature. We know that the specific heat of water is 4.2 and that the system reaches equilibrium once it reaches a temperature of 100 degrees Celsius. So through the energy principle and the specific heat equation, we can find that E thermal is equal to mc delta T. And through these calculations, that the change in thermal energy of the water is equal to 739,200 joules. Now in part B, we must use this information to determine the transfer of energy into the system from the surroundings. Again, we must note that the electric beater does 100 joules of work each second during its 15-minute measured time interval. And again, through the energy principle, we can use this to isolate Q and therefore determine the work, so that we can find Q in the end. So by the same fundamental principle, which is the energy principle, we find that Q is equal to the change in thermal energy minus the work done on the system. And we find that work is equal to the 100 joules times the 900 second time interval over which the beater is doing work on the system. And by subtracting this from the thermal energy we found on the previous slide, we find that Q, the transfer of energy into the system, is 649,200 joules. Now in part C, we have to reference back to part A in order to determine the answer. We know through our fundamental principle that the energy of the system the change in the energy of the system plus the change in the energy of the surroundings is 0 within a closed system. There is no energy lost, it's all conserved. So through this method, we know that the opposite of the change in energy of the system is equal to the change in energy of the surroundings. Therefore, the change in energy of the surroundings is just the opposite, or negative 739,200 joules. Part D is where this problem steps up its game and asks you to require more knowledge about the system. So they give you this information in addition. You take the pot off the stove and drop in 2.26 kilograms of sweet potatoes. The potatoes are initially at room temperature, which is 25 degrees Celsius, and have a specific heat capacity of 3.14 joules times grams over degrees Celsius. You must determine the final temperature of the water and the sweet potatoes once they reach equilibrium. You can assume the pot is a very good insulator and does not change temperature. So through our same fundamental principle, the energy principle, we know that the work plus the transfer of energy is equal to 0. And we know that this change in energy is equal to the specific heat of the water and the sweet potatoes once the two reach equilibrium. So we take mc delta T of the water plus the mc delta T of the sweet potatoes. You have to find the final temperature of the system combined. That is the final temperature of the system, which is the sweet potatoes and the water, which is denoted as TF. And through these calculations, you can see that I solved for the initial TFs, well, not initial TFs, but TFs, and then also the other degrees Celsius. And when putting like terms together, I determined that TF was equal to 65.65 degrees Celsius. So to answer the question, the final temperature of the equilibrium system between the potatoes and the water is 65.65 degrees Celsius. This concludes the presentation of exam wrapper 2. Thank you very much.